Good morning, everyone in Algebra 2. Let's get after this function operations, part 2. Let's get after these composite functions. Yesterday, remember, we did addition, subtraction, multiplication, and division. Today, we have just one function, but it's brand new. It's not that difficult if you pay attention, but if you don't, since it's brand new, you'll have no idea what you're doing. So watch this from minute 1 all the way up through the very last second, please. All right, so remember yesterday I said be careful when you're doing multiplication to make it just a dot and not a circle, because the circle means something different. Well, here's what that different is. It's called a composite function. So G with this little circle and F means that you're really taking f of x and you're finding the function G and applying that to what you get from putting in f of x. This will make a lot more sense once we have an example, but the key to this is that the order of these functions matters, and when you put the composite function looking like this, it means this, which means that as always you work from inside, the furthest inside a set of parentheses first. So you're going to do whatever this thing is first, and then you're going to apply the g function to it. Now, as I said, this makes a way much more sense once we have an example, so we're going to do an example here. Now, you have to have two functions that are defined, so we've got f of x defined as x minus 5 and g of x defined as x squared. And we're supposed to find g of f of negative 3, g of f of negative 3, the composite function g of f, and apply it to negative 3. What that looks like is this, is that we do the f function first. So we need to find f of negative 3. That tells us look at this function and plug negative 3 into this part, like this. This part right here is nothing new. We just need to combine it with something else. So we've plugged this negative 3 in, and we find that we get negative 8. That's not your final answer, though, because from here, what this means is that I need to plug negative 8 in to the g function. You're really finding g of negative 8 because that's what you got when you plug negative 3 into this function. So I plug negative 8 into the g function. And when I square it, I get 64. And that is the answer to the composite function g of f of negative 3. So as long as you do your steps, the actual calculations aren't so bad, but you have to know what to do and in what order. First you rewrite it, then you do this function, take what you got, plug it into the other function, and you've got your answer. Let's see what happens when we use the same functions, but you reverse the function order. So if I take f of g of negative 3, well, here you're going to do the g of negative 3 first. Same g function, okay? But look, we're doing it in the opposite order. So you're going to take negative 3 and use this function. So you're going to square it, because g of negative 3 is negative 3 squared, and that gives you 9. Once you have the 9, you're trying to find the value of the function f when x is 9. So we plug that in, f of 9, and you plug that into the other function. 9 minus 5 equals 4, and the answer to this composite function for negative 3 is 4. f of g of negative 3 is 4. Now these looked very much the same, but let's look at these answers right next to each other. g of f of negative 3 was 64 by our calculations. F of g of negative 3 is 4 by our calculations. So what that tells you is that function composition is not commutative. It does matter what order these are in as far as what gets applied first. So don't have tons of examples for you this morning, but as you go through and as you do the assignment, you're going to be able to practice, and I would suggest going back over this since this is completely brand new, and follow the steps. Let's look at another one. This one's the same two functions to deal with, but what if we're using the general case? We figure out the general case so that in case you have a whole bunch of values that you need to plug in, you can always just jump right to the composite function that includes a variable. So again, we're trying to find g of f of x. F of x is x minus 5, so I can put my x minus 5 right in here. So what this tells us is I need to take x minus 5 and put it in where x squared is. X minus 5 squared, don't forget it's not just x squared minus 25. You've got to multiply that thing out because it's a binomial squared. It follows the pattern this one squared at the beginning, this one squared at the end, and 2 times these. If you need to write that out and do the multiplication, x minus 5 times x minus 5, do that for yourself to convince yourself. So here is what we finally get for an answer for that. And I have x squared minus 10x plus 25. So if I had a whole list of numbers that I wanted to plug in for x here, I'd have this function without having to do the one function and then put it in the other function. Same with f of g of x. F of g of x means that I need to take f of x squared, which means the x squared goes in here where this x is. And so my final composite function is x squared minus 5. When you're given an individual number, you're just getting one of the values of the composite function. When you are doing this process, you're actually writing the composite function. Okay, I'll say that again. The numbers, when you plug in the number, you're getting a value for the composite function for just that one number. When you actually do this process, you're finding the composite function. Okay, and we would use this if you have several to solve. So I want to look at one example with you as far as where a practical application could come in for this, because a lot of times people will have deals and coupons and things like that, and the companies are very smart as far as what order they apply the coupons and the discounts in, and they've done things to figure out which is going to make a difference. So if you ever have your own small business, you're going to want to have the coupons applied in a way that's best for you and train your employees correctly so that your business is always consistently coming up with the same number. Okay, so this happens to be a pizzeria. You have a coupon good for $5 off any large pizza. You get a 10% discount off on any pizza if you show your student ID. How much would you pay for a large pizza if the cashier applies the coupon first? How much more would you pay for a large pizza if the cashier applies the coupon first? So there's two possibilities. Either they're going to apply the discount first and then the coupon, or the coupon first and then the discount. We're going to look at that in terms of composite functions, because you might be thinking, wait, but I don't know how much the pizza costs. Doesn't that matter? Well, actually not if we think about it with composite functions. So this would work for really any price for the pizza. Even if the pizzeria raised its prices on a pizza, you're still going to have the same how much more you would pay, and I'll show you why. So X would be the normal pizza price. C, this is going to be our coupon function. So what happens with the coupon? The coupon is $5 off, so that means the pizza price minus $5. D of x is the discount function. This would be if just the discount were applied. You would have the original price minus 10% of the original price. 10%, decimal over twice, is 0.10 times x, and that would give you 90%. So you would actually be paying 90% of the cost of the pizza. Our coupon first composite looks like this. D of C of x. D of C of x. Should really be some parentheses around here, but this is where you apply the coupon first. So in other words, you're taking the discount function, applying it to the coupon function. So this gets put right in here, 90% of x minus 5, and that gives you 90.90x minus, I put it in money terms, minus 450, because 0.90 times 5 is 450. If you do the discount first, you reverse the order. So we're trying to find the coupon function of the discounted price. So this goes in here, and I have 0.90x minus 5. Now it says, how much more would you pay for a large pizza if the cashier applies the coupon first? Okay, so here's our coupon first function, and here is the discount first function. So we're taking our coupon first function, because it says we're paying more for that, and we're subtracting our discount first function. How much more would you pay for the large pizza if the cashier applies the coupon first? Okay, so here's our coupon, here's our discount function. So when we subtract those, what we find is these two cancel out, and negative 450 plus 5 gives you 50 cents, 0.50, 50 cents. So no matter what your menu price for your pizza was, if you apply the coupon first, in this case, you're going to pay 50 cents more than if they applied the discount first. So, and here you can even look at the functions to kind of tell which would be the better deal. Both of them involve 90% of the cost of the original cost of the pizza, but coupon first is only taking $4.50 off of that price. Discount first takes $5 off of that price. So either way you look at it, you have the information now to figure out which is going to be the better deal, and then also how much that's going to cost you if they do it in the opposite order. And so as a business owner, you're going to want to do the thing that gets the business more money. So you would want, the cashier would want to apply the coupon first. And I actually ran across that in a store where they were doing it one way one time and then another way another time, not for pizza but for something else. And I said, well, wait a minute, last time I was in, you applied it this other way, and I paid less for it. And so I had them do it that way, but then they changed their policy to make it better for the store. So anyway, that's it. That could be useful for you. And I hope that you have understood this. Keep in contact. Keep doing what you're doing. Stay healthy and safe. And I hope to have us all through this very, very soon. Have a great day.